Hi, how are you doing? My name is Lonnie Palam, and today we're going to discuss the gas laws. Those gas laws would include Boyle's gas law, Charles' gas law, Gay-Lussac's gas law, and the last one would be the combined gas law. Okay, so let's begin with Boyle's gas law. Boyle's gas law. Let's state it here. Well, what does Boyle's law, or Boyle's gas law, what does it state? It states this, that for a given amount of gas held at constant temperature, the product of pressure and volume is a constant. So what does that mean? That means that pressure times volume is in fact equal to a constant. Now, in terms of the conventional way of expressing Boyle's law, we can therefore identify this equation and translate it to P1V1 equals P2V2, and this in fact is the conventional way of stating Boyle's law. Well, what does that tell us? There's a couple things we want to know. We know that in fact, if pressure increases, what effect will it have on volume? Well, the volume will in fact decrease, or vice versa. If volume increases, what effect will that have on pressure? Pressure is going to decrease. This type of relationship is known as an indirect relationship, or that they vary indirectly, or that they are indirect variation or indirectly proportional. So all of those are synonymous. So let's go ahead and move forward and let's do a problem. And we are going to start with example one on page 443. And this is a Boyle's law problem. Example 1 on page 443. Let's read the problem. It states, a diver blows a 0.75 liter air bubble 10 meters underwater. As it rises to the surface, the pressure goes from 2.25 atm to 1.03 atm. What will be the new volume of air in the bubble at the surface? Okay, what's the first thing that we do in any of these type problems? The first thing is let's identify the known versus the unknown. Well, the given information or known information that was given was, first of all, the volume 1 was 0.75 liter of the air bubble. Pressure 1, P1, I'm going to specify it as P1, was given at 2.25 atm, standard unit for atmospheric pressure. We were also given that the pressure changed from 2.25 and it in fact dropped to 1.03 atm. And in fact, when we scroll that up, we are looking for the new volume of air at the surface as it rose to the surface. Well, let's put this in a calculative format. Remember, here's Boyle's law. P1V1 equals P2V2. Note, initial conditions P1V1, new conditions P2V2. And let's go ahead and rearrange this. I know that I've got to solve for V2, so I'm going to isolate V2 and write it in terms of the other variables, P1V1 divided by P2. Let's go ahead and add the data that we have. Pressure 1 was in fact 2.25 atm. My volume that was given was 0.75 liters. So here's what we have. In the denominator, we need pressure 2, and pressure 2, in fact, was decreased to 1.03 atm. When we do a calculation, we will, in fact, let me scroll that down a little, V2 will, in fact, equal 1.6 liter. 1.6 liter. Now, the question was this, let's see if that, in fact, worked. Boyle's law says temperature is held constant, but that the quotient, that there is an indirect relationship between pressure and volume. Well, pressure was 2.25, dropped to 1.03. Volume tells us that with the drop in pressure, pressure decreased and volume should increase according to the original, and with respect to the original volume. Did volume increase? Yes, it went from 0.75 to 1.67. So that, in fact, is the relationship between pressure and volume for Boyle's law. All right, let's continue on, and let's go ahead and let's talk about our second law, which in fact happens to be Charles' law. Okay, now what does Charles' law states? Charles' law states that for a gas held at constant pressure, the quotient of volume to temperature Kelvin, in fact, is equal to a constant. So let's write that in terms of variables. Volume with respect to temperature in Kelvin is equal to a constant. Well, note that this so likewise can be written in this format. Again, initial conditions versus new conditions. So volume 1 versus temperature 1 is equal to volume 2 versus temperature 2. Now what does this tell us? Well, here's a couple of things that we need to know. Note that volume and temperature are in fact a direct relationship. So in fact, if one of those increases, let's take volume, what's going to happen to temperature? Temperature so likewise will increase. So knowing that, going into this next problem, we are going to do example 2 on page 446. Okay, let me go ahead and read the problem to you. This is Charles' Law, example 2 on page 446. It states, a helium balloon in a closed car occupies a volume of 2.32 liter at 40 degrees centigrade. If the car is parked on a hot day and the temperature inside rises to 75.0 degrees centigrade, what's the new volume of the balloon, assuming pressure remains constant? Well, again, just as in Boyle's law, one of the first things that we want to do is state the given information. Well, what was given to us? Well, we were given initially that that balloon, in fact, had a volume of 2.32 liter. We know that the temperature in the car was, in fact, 40 degrees Celsius, converted into Kelvin would be 313 Kelvin. Note that temperature must always be converted into Kelvin as we do these types of calculations. We were also given a temperature 2, and that temperature 2 was the temperature had increased from 75 degrees Celsius, from 40 up to 75. The conversion in Kelvin would in fact be 348 Kelvin, and our unknown is volume 2, and this is what we're looking for. So let's go ahead and write the initial conditions and new conditions for Charles' law, which is V1 to T1 equals V2 to T2. Well, let's go ahead and rearrange this. We are looking for V2, that's my unknown. So let's isolate V2 and rewrite this. Hence, V2 equals V1 T2 divided by T1. Now we can plug in the data that we've been given and solve for our V2, so let's go ahead and do that. Well, my V1 was given at 2.32 liter. My temperature 2 was in fact increased to 348 Kelvin. Okay, and we're going to divide that by the initial temperature, which was 40 degrees Celsius, or 313 Kelvin. Once we do a calculation on this, note that our new volume will in fact be 2.58 liter. 2.58 liter. Well, originally we had 2.32. And it now increased to 2.58. Well, we know that it is a direct relationship, volume to temperature. So volume increased, so that tells me that also temperature must have increased also. Well, my original temperature was 313 Kelvin, or 40 degrees Celsius, and it in fact increased to 75 degrees Celsius, or 348. This in fact has been verified, Charles' law. So we're good. Let's go ahead and let's continue on. We're going to do the third law. And the third law is Gay-Lussac. Gay-Lussac, okay? This is the third gas law, Gay-Lussac law. Okay, what does the Gay-Lussac law state? This is what it states. For a given amount of gas held at constant volume, this is a little different from Charles, but held at constant volume, the quotient of pressure divided by temperature in Kelvin, is in fact equal to a constant. So what does that mean? Let's state that. The pressure divided by temperature, or the quotient of, is equal to a constant. Well, we know that also this can be rewritten in the initial conditions versus new conditions, which is the standard or conventional way of expressing Gay-Lussac's law. So let's rewrite this. So hence we can say P1, T1, initial conditions, is equal to P2, T2, new conditions. Great. So now we've stated Gay-Lussac's law. Let's go ahead and do a problem. And the problem that we want to do is problem example number 3. Example number 3 on page 448. Example number 3 on 448. Let me go ahead and scroll that up so we have a little room to work with. And let's go ahead and proceed on this. I'm going to read the problem, and here it is. The pressure of the oxygen gas inside a canister is 5.00 atm at 25 degrees Celsius. The canister is located at a camp high on Mount Everest. If the temperature there falls to negative 10 degrees Celsius, what is the new pressure inside the canister? Well, let's write this data and information that was provided us. Obviously, the first step in calculating the unknown. Well, they gave us a pressure originally, and that pressure was 5.00 atm. Okay? They also gave us a temperature, and that temperature, T1, was expressed in Celsius. So we're going to convert that to Kelvin, 25 degrees Celsius, which in fact is the same as 298 Kelvin. Let me scroll that up a little more. They also gave us a second temperature. And that canister actually dropped, and it dropped to a negative 10 degrees Celsius, which in fact is the same as 263 Kelvin, and hence, let me scroll that up a little more, give us a little more room, and hence we are looking for the new pressure in that canister. That is my unknown. Okay, so let's go ahead and let's restate this in terms of Gay-Lussac. P1 to T1 is equal to P2 to T2. Initial conditions, new conditions. Let me scroll that down just a hair. Okay, we're looking for P2. That's my unknown. So let's rearrange this. Hence that P2 is equal to P1 T2 divided by T1. And hence we are ready to plug in the data that was originally given to us to solve for our new pressure. So let's go ahead and plug in the values there with the units. Okay, the values are, in fact, P1 was stated at 5.00 atm times T2, temperature 2, was in fact 263 Kelvin. Of course, it decreased. The original temperature was 298 Kelvin. Okay, now we can do a calculation and then solve for our new pressure there at the top of Mount Everest. So P2, therefore, equals 4.41 atm. Okay? Well, let's see if that in fact follows the direct relationship that's stated in Gay-Lussac's law, that pressure is directly related to temperature. If temperature goes up, pressure goes up. If temperature goes down, pressure also goes down. Well, let's look at the original pressure. Well, let's look at the temperature first. The original temperature was, in fact, 298. It went down to 263. So what does it tell me about my pressure in terms of that we're solving of P2? My pressure must also go down similarly, an indirect relationship to what happened to temperature that went down. Our new pressure was in fact 4.41 atm. Did it go down to the original 5.0? Yes, it did. We have solved utilizing Gay-Lussac's. Okay, we're going to do one more law here. And that last law is called the combined gas law. Combined gas law. Okay, combined gas law. Now, the combined gas law states this. For a given amount of gas, the product of pressure and volume divided by temperature, again, temperature in Kelvin, is equal to a constant. Well, let's rewrite this as we've done with the other laws. The product of pressure and volume divided by temperature is equal to a constant. Now, again, as we did with the other laws, we can rewrite this in terms of initial conditions and new conditions, and hence the conventional way of which the combined gas law is expressed. So hence, P1 V1 divided by T1, in fact, is equal to P2 V2 divided by T2, and hence the combined gas law. Well, let's go ahead and work a problem on this. And we're going to do problem number 4, example number 4, and this is located on page 450. All right, let's go ahead and read this, and we'll move ahead. The problem states as such. A gas at 110 kilopascals, note we have a change in atmospheric units, kilopascals, and at 30 degrees Celsius fills a flexible container with an initial volume of 2.00 liter. If the temperature is raised to 80 degrees Celsius and the pressure increases to 440 kilopascals, what's the new volume? Okay, well, let's go ahead and let's first write the data that was given us, okay? Originally, we were given pressure 1. Pressure 1 was stated at 110 kilopascals, okay? We were also given temperature 1, and temperature 1 was stated at 30 degrees Celsius, translated to Kelvin would be 303 Kelvin. We were also given volume 1, and volume 1 was, in fact, 2.00 liters. Okay, we're almost there. In addition, we were given a new temperature. That new temperature was, in fact, 80.0 degrees Celsius, which translates to 353 Kelvin. Again, we were given pressure 2, which increased to 440 from 110 to 440 kilopascals, and hence we are looking for volume 2. Here's our unknown. That's what we're looking for. Okay? So far, note we've got all of our data that we were given in the problem, and we are solving for V2, or the new volume. So let's restate this. Let's state the combined gas law of P1V1 divided by T1 in fact is equal to P2V2 divided by T2. Our unknown again is V2. Let's rearrange this such that V2 is expressed in the other variables. So let's do that. Let me scroll that up a hair and we'll give ourselves some room. So hence V2 is equal to P1V1 T2 divided by T1 P2. And hence rearrangement. And sure that's correct, V1? Yes, that is correct. Now let's go ahead and plug the data in here that was given to us originally in the problem. And so hence, I'm going to write it down here. We need a little more room, so I'm going to go directly below this. So equals, all right, P1 in fact was 110 kilopascals times V1. V1 was, in fact, was given 2.00 liter times T2, and T2 was in fact 353 Kelvin. So far, so good. Let's do the denominator, T1. T1 was expressed at 303 Kelvin times P2, and P2 was expressed at 440 kilopascals. Let's go ahead and do our calculation for this so we can solve for our V2. And when we do the calculation, we in fact, for V2, our final answer is 0.58 liter, and that in fact is the solution for our combined gas law. Thank you very much for your time. Bang, and that's a wrap.